So let's start stage 2. So opponent, please challenge.
We want to challenge problem number 4, primary movement. Please reject.
That's number 4, reject.
Problem number 2, air muscle.
Okay, number 2, accept. And please write your name on the blackboard.
Ready? I'm ready.
Okay, so reporter, please start.
Hello everyone, I'm the reporter from variable 1, and today I'm going to report my research on problem 2, air muscle. This is the following statement. Place a balloon inside a cylindrical net and sometimes use red garlic and inflate it. The net will expand and shorten. Investigate the properties of such a muscle. In my experiments, I will focus on the stiffness parameters of the muscles. This is the first theory. In this formula, you can see that the F is the force the muscle generates, and the R0 is the initial nominal radius of the muscle, and the P is the interpressure, while epsilon is defined as L0 minus L divided by L0, and the L0 is the original length, and the L is the length after it is inflated, and alpha is defined as this, and beta is defined by this. By the way, the theta 0 is defined as the angle, which is the center axis of the muscle and the brace angle. This is the second theory. When an air muscle or a spring is applied by a tensile force, it will exhibit a similar behavior, which means that it has a quite similar formula, but it's quite different because the stiffness of the spring depends on the material more than, and the stiffness of the muscle depends on more variables than just that. This is the formula of the second theory. In this case, the F is the force the muscle generates, and the K is the stiffness. And the P is the interpressure, and the LS is the stretched length, and Q1 to Q4 is just constant that should be found in the experiment. And this is my experiment direction. First, I will find the information from the first theory, and then I will use the data to find out the information in the second one. And this is my equipment and setup. It mainly contains an air pump, a spring scale, and a muscle, and other components. First, I will tie the two sides of the muscle on two single points, and then a soft straw which is connected to the muscle will be the way I inflate the muscle. And this is my procedure of first, I will pump air into the muscle and inflate it while recording the process. Then I'll be able to measure the data by imaging. And this is my data of the muscle 1. The R0 equals 1.8525 centimeters, and alpha equals that, beta equals that. And this is the chart of the force. This is the every amount of time I measured this, and this is the force. Well, that is the chart of the epsilon. This is the every amount of time I measured it, and this is the epsilon. Epsilon is a rate, so it doesn't have a unit. This is the experiment data of muscle 1. I used the previous data to calculate the pressure per time. And this is the chart of the pressure. And this is the experiment data of muscle 2. The R0 equals this, and the alpha equals this, and the beta equals that. And this is the chart of the force. And this is the every amount of time I measure it, and this is the force. And this is the every amount of time I measure epsilon, and this is the epsilon. Again, epsilon is a rate, so it doesn't have a unit. And this is the experiment data of the pressure for muscle 2, and this is the chart. The x-axis is the every amount of time I calculated, and the y-axis is the pressure. This is experiment 1's results. From experiment data, we can obtain the pressure every time. Then we use the data in the second formula to investigate stiffness. In this formula, we can see that the F elastic is the force generated. So we are going to measure it, and then we'll find the characteristic of the air muscle. And these are the two muscles I pick out to explain this behavior. And this kind of muscle is more like a sphere, and this one is more like a cylindrical one. And for the procedure, I will first compare into the muscle while recording the process, and then I'll measure LS and F. And the F is the force that shows on the spring scale, and then I'll use data to model the 3D diagram by Python. This is the parameters meaning of K's constant. First, the Q1 is the material impact, and the Q2 is the length direct impact on the stiffness, and Q3 is the interaction between the pressure and length, and Q4 is the pressure's direct impact on the stiffness. This is the procedure of experiment 2. First, I'll calculate the Q1, Q2, and Q3, Q4 by Python, and then after I input the data, the parameters can be calculated and given back, just like the code written here. And this is the second step of my calculation. First, I'll model the 3D picture with the parameter given previously. I'll define the function first, and then I'll input the parameters which I just calculated here, and then it will draw out the 3D diagram. This is the results of muscle 1. As you can see, the Q1 is bigger than 0, meaning that the material impacts positively. And Q2 is also bigger than 0, meaning that the stiffness and the muscle deformation has positive correlation. And Q3 is smaller than 0, meaning that the stretcher length and the pressure together impacts negatively. And Q4 is bigger than 0, meaning that the stiffness and the pressure has positive correlation. And that is the chart of the 3 measurements I just measured, and then this is the LS, and that is the pressure, and this is the stiffness. And this is the result of muscle 2. As you can see, the Q1 is bigger than 0, meaning that the material impacts positively. And the Q2 is also bigger than 0, meaning that the stretched length impacts positively. And Q3 is smaller than 0, meaning that the stretched length and the pressure together impacts negatively. And Q4 is bigger than 0, meaning that the pressure impacts positively. And that is the chart of the 3 things. And this is LS, this is the pressure, and this is the stiffness. This is my discussion. According to the 2 air muscle, which I picked out, we can know the characteristic of all sort of muscles. First, the Q1 is mainly bigger than 0, meaning that the material impacts positively. I think this is correct because most of the things you like the spring, if you stretch like this, it's go like this, so it actually impacts positively. And Q2 is bigger than 0, meaning that the stretcher length impacts positively. And Q3 is smaller than 0, meaning that the stretcher length and the pressure together impacts negatively. And Q4 is bigger than 0, meaning that the pressure impacts positively. And for the Q3, this one, I think it is because of the geometric model of the muscle. And this is my conclusion. The air muscle properties is related to the stiffness, and the stiffness is related to the muscle type, and also the stretched length and the pressure. And these are the references. And thanks for your attention.
Okay. Opponent, please ask a question.
Near to the conclusion page. You mentioned that there's three factors that affects
The stiffness,
yes, the muscle type, the stretch length, the pressure. However, did you quantify it?
what do you mean quantify? It can be quantified because muscle type is just like this type of muscle and do this and that.
And how about the stretch length?
Stretch length is measured by imaging.
Okay, then the pressure.
The pressure is calculated in Formula 1.
Okay. You want to talk about the stiffness, right?
Yes.
Did you quantify the stiffness?
Stiffness is
You don't think I can quantify, right?
the stiffness has a clear definition, which is the stretches force divided by how long you stretch it.
Yes.
So you don't need to quantify it because it has a clear definition.
Yes, so did you consider using the Young's module? Why? Why?
It's not important.
You think not inferring the Young's module is not important, but however, Young's module is to describe the fitness of the material. So why do you're talking about the stiffness, but you don't want to use Young's module?
I want to use the constant here, like Q1 and Q2 and Q3 and Q4 to investigate the stiffness, but it is nothing about the Young's models.
Okay, so you think that Young's module is no relationship with this problem?
No, I use the stiffness to investigate it.
Okay.
So
Time's up. please start if you are ready.
I'm the opponent from Yamaha, and this is the problem statement. And the points that the reporter focus on is the stiffness parameter of the muscle. And this is a brief summary of the reporter. Their observation in the theory is the stiffness parameter of the muscle contain too many variables in the theory compared with the spring. And their experiment method is using an air pump spring scale drop, but however, they didn't standardize the balloons. And their data analysis is unclear demonstration of the relations. And their conclusion is the stiffness is decided by the muscle type, stretch length, and the pressure. And for the pros and cons, the pros of the reporter is that they have clear explanation and thorough PowerPoint. But however, their experience data is unstandardized and fail to have a theoretical conclusion. And let's jump to the next slide. Can you turn to the first theory page? Yes. You assume that, in this theory, you assume that that's a cylinder, right? But
In this
however,
theory,
what?
you mean in this theory?
Yes.
Yes.
But however, if you have an experiment that you use as a fair muscle, as a fair balloon,
Yeah.
and that's
What do you mean why I
Very
use
dark.
this? This is because that it only, in the problem statement, it only mentioned that the nets need to be cylindrical but not balloon. So I think.
no. I mentioned that your theory is suppose that the balloon is cylindrical.
No.
No.
I think both of them is suitable.
Okay. And did you always use the same balloon for the whole experiment?
You mean which experiment? Sorry.
All of it. You use the same balloon?
Experiment 1 for one muscle, experiment 2 for one muscle. Can you clarify that?
Okay, for example, the first experiment and the first muscle.
The first experiment, every time I do the experiment, I change the muscle because I bought a lot of the same one.
Okay. And can you turn to page 15? Can you explain why is there like 13? 13. Can you explain why there's a limit?
What do you mean?
There's a certain, it's not linear, right?
Yeah.
Why?
But the pressure doesn't have to be linear because the shape will change.
Yes, but I know. Why? Tell me why about
The shape will change.
the shape will change, so that's why there's a limit.
Yes.
We believe that there's a limit is because the net outside the balloon will restrict the balloon's inflation. So that's why there's a limit.
Yes, that is also a reason.
That's also. Okay, turn to page 10. Why is that negative? That's fine. Why is that negative?
Because when the net expands, the muscle from this side, the vertical side will shrink.
Oh. But when the t equals to 0, it's negative. You assume that?
So where is it? Oh, that is just close to 0, not actually 0.
And would you consider talk about the stiffness, the balloon and the, sorry, the net and the balloon's relationship, about their stiffness.
For my experiments, I think the whole muscle should be
So
considered
you're,
in Q1 if it is not inflated. When the stretched length and the pressure is 0, the whole muscle should be seen as the one system. So the stiffness of it should be seen as Q1. So you don't have to separate it.
okay. Then, do you consider changing another material for the mesh? What do you think it will change? Change the material of the mesh.
No, because when you change the material of the net, the result will change. But I think you should say
It's considered as
you should make it stable, or the result will change and you can't find the relation between it.
you can have different type of muscle, right?
Yes.
So why don't you consider another material of the net in the same balloon?
That is not our main focus.
Okay. May I just check?
Yes.
And the shape is our main focus on our
Yeah, I do.
experiments.
Can you draw the diagram? What will observe?
I can't just draw it because I didn't measure it, but I believe it will go like positive. Because when the volume of the balloon like increases, it will stretch from both sides and then force it.
Yes, but remember I just mentioned that I believe that there's a certain limit boundary that it won't keep the volume of the balloon. The volume of the balloon won't keep going up because if it's too big, then the balloon will just explode.
Actually, I did an experiment before, and it does, but it will stay like, say, here's a point, and it will explode, and then I don't know because it just explode. Yeah. What
I
do you think
suggest
about
that
this?
you should do it. You should put it in there. And also, and why is there a limit is that I just mentioned, but I asked you this question, you didn't answer me. I just said that that's because the match is given the force to the net.
Yes.
So that's why there's a limit. There's a certain limit.
Yes.
And can you turn to your experiment setup page? What did you use to inflate the gas?
An electronic pump. Have you seen it before? It's like
Yes, I know.
a pump.
But you know that it won't be the. Can I go to a thermal station? Extend and short, and it will be this and this, right?
What do you mean?
If you, sorry, if you inflate the gas in, or if you leak out the gas, then it will be different size, right? I know. Be different size, right? Did you consider in your experiment?
No, that's nothing about my experiment.
Okay. And how about how do you make sure that the gas won't leak out in your experiment setup?
As you can see, I use components to tie the where I tie
Yes,
it, and then tie it very
How do
tight.
you double check? Do you think, I believe that you should double check because if the gas leak out, you can't actually see it, right?
Yes, but I need to say that when you do the experiment, the gas pump in, and then as you take out the electronic pump, and then you like fold the straw, And I can see that it won't leak out the gas, so I believe it is very tight.
In my suggestion, I'll suggest you put the air muscle in the water so that when you pump the air inside, if there's gas leak out, then it's very obvious in the water.
Oh, in my previous research, when I do the experiment with the water, I try to measure other things. I did it before, but it doesn't leak really.
Yeah, I suggest you put it in your experiment, not just say you did it before. And did you consider the gap between the gap between the mash and the balloon?
What is the You don't have to consider it because the R0 is like when you use this theory, you have to make sure that the muscle is still use the right way.
Sure.
When you use a theory here, you have to make sure that the muscle is going like this, have no gap between the legs and the muscle.
How do you make sure? And if you think that there's no gap, then how do you make sure that there's no fold in the balloon, between the balloon and the neck?
I mentioned that I record the process, the whole process, so I can see it from the video.
So you recorded 360 degrees for the whole balloon.
Yes.
How do you record it?
I have two camera, and then I put it here.
This camera, but you put four sides. Please go to the experiment setup part.
Okay.
One second. This is not. Yes. There's gap between them.
Yes, but this didn't touch the muscle, so you just only need to consider here. So you know when
Didn't touch the muscle. So what's your identifiable muscle? How about you consider a thicker mash and a thicker balloon so that you can make sure that there's no gap between them.
that's a good suggestion, but I think you should inflate it and make sure it does.
And you didn't check. You said you used 300 degrees. 300 degrees. Yes, but you should. Your experiment setup is not clear. You know that. So it's really confusing. I suggest. Sorry, but I suggest you can explain it more complete in your future. And also. That's all for my questions.
Okay. Opponent, please summarize.
Okay. We have talked about the gap between the mash, and they says that they have reported to make sure that there's no gap between them. But however, that's very confusing and doubtful. And we also talked about that consider using the Young's model. However, they don't think that this is necessary, and also we have talked about that they use a cylindrical and spherical balloon. But however, in their equation, it seems like they assume the balloon is cylindrical, so that's a little bit confused. And also, they talk about they use the image J, but however they didn't actually deeply just introduce.
Okay, time's up. Okay, reviewer, please ask
questions? Reporter, can you go to slide 22? So here you explained how the characteristics would change if Q was positive or negative, but I want to know how would the magnitude affect the characteristics?
The last sentence.
How would the magnitude affect it? Like, say it's already positive, but what if the value goes up? What would happen?
No, it won't go up because it's the original muscle that is not inflated, which has no stretch length and no pressure in it. So it's unchanged.
Are you saying it's constant?
Yes, it is. I'm very sure.
Okay. Can you go to the epsilon versus time graph?
Which page is it?
Just go to your graph.
Which graph?
Epsilon versus time. Go ahead. Yeah. Can you explain what the purpose of this is? What are you trying to find?
To show that I did measure the experience.
What conclusion are you trying to make?
Because I want to use the data I mentioned before to calculate the information.
Don't you think there would be some other focuses that would be more important?
No, because in the, I'm sorry?
Yeah, than calculating epsilon.
Because in the theory mentioned before, it's only these that is in the formula, so you don't have to consider other factors.
What is the significance of the magnitude of the constant as a coefficient? Okay, it's fine. I have a question for the opponent. Like, you mentioned that you would submerge the balloon in water to prevent leakage. How would you account for the water pressure?
Account the water pressure?
Yeah.
No, I'm just saying that I put it in the water. It's just looking that the gas leak out or not. And if the gas is not leaking out, then I will just put it out of the water and keep doing my experiment. I'm just doing a check. Do you understand? Because if there's gas leak out in the water, there will be a bubble. And
I
it's
see.
kind of obvious.
Then what parameters do you think are the most important? They mentioned stiffness being the most important parameter, but what do you guys think?
I think that there's tons of important parameters, and I think one of them is the gap between the balloon and the mesh, and also the diameters of the mesh, and also
Sorry.
the length of the mesh.
Yes.
self-reviewer. Please take the floor.
Hi, I'm Steven, and I'll be reviewing the air muscle for the electives. So here's the problem statement, and the main focus the reporter decided to focus on was the stiffness of the air muscle. Here was the reporter's performance. Their phenomenon was comparing a balloon that acts similar to a spring where there's elasticity. The theory was that air muscle exhibits similar behaviors when tensile force is applied, but stiffness is the main factor. And in their experiment, they recorded force over time and they used it to calculate pressure. And the pros were that it was a pretty clear explanation of their variables. There was 3D analysis and they used Python simulation, and the slides were pretty organized overall. However, some of the cons were that the derivations of the formulas were unclear. I had no idea how they really declared any of their equations. The shape of the balloon is unclear in the slides. They mentioned that there was spherical as well as cylindrical shapes, but they never mentioned which graph corresponds to which balloon. And also how they calculated pressure is unclear. They just showed like force over time. I have no idea where they got their pressure from. And the behavior is explained unclearly. They didn't explain the magnitude of the coefficients. There's no error analysis, and there is an incomplete conclusion. The opponent's performance, they mentioned missing parameters such as the Young modulus, assumptions in their analysis, and they analyzed data trends and potential errors in the reporter's research. Some pros are that they offered their own opinions and methods such as testing for leakage, and they questioned the limits of the reporter's research. They could have spoken with a clearer voice though, and they could have discussed the reasoning behind the reporter's conclusion even deeper. The first thing they asked about was that whether or not the reporter assumed cylindrical shape for their balloons. The reporter said no, it could have been cylindrical, but it doesn't have to. And I think that the reporter should be more clear on the shape of their balloon as it affects the volume and therefore the pressure calculations, which is a crucial part to this topic. And secondly, the opponent asked why is the graph non-linear, and the reporter just said like the pressure changes. I don't think the reporter really has a clear understanding of the graph, because from my experience and my knowledge on the topic, after a certain extent, after it reaches a certain threshold, the pressure sort of remains constant, sort of a logarithmic relationship, and then if it exceeds the threshold by too much, the balloon would pop, and I think the reporter failed to address that. And then the opponent asked, did you consider changing the materials and what will that affect? The reporter said that they should keep the net constant because that's not their focus, and I can understand why the reporter doesn't want to include another variable into their experiment, but I think they should have at least accounted for this, maybe as an assumption or an error. And then the opponent asked, does the balloon change size? And the reporters said they didn't consider this. I found this pretty strange because changing the size is very important in calculating volume and pressure. And then some additional topics they discussed: gas leaks. Like this, the opponent suggested an underwater method. I think this is pretty necessary because gas leakage would cause a completely different expansion and volume. And I think they could have done more to explain critical values. And they didn't really explain the characteristics of the graph. They just explained if the sign is positive or negative, what would happen. They didn't clearly explain the behaviors or the magnitude. Yeah, thank you.
The reporter, please conclude.
I have to say that in the previous questions, the opponent asked me about the Young's modulus, but it is considered in the Q1 and Q2 and Q3. And in our setting, we consider Young's modulus inside the Q1 to Q4 which explains stiffness. And the theory, we think the theory is most suitable for cylindrical and sphere balloons. And P is not linear, the shape change, but we just need to calculate. And when stretching the muscles shrink in the vertical direction. And material, different type of muscle depends on the shape, but not the material. And the FV graph, we agree there is a limit, but we do experiment before the balloon explodes. And first, about the gas leaking, we did the experiment in the water to make sure the gas doesn't leak out. But that is the previous experiment, so we didn't add it in our report. And gap between the net and the balloon, we record from 6 direction to ensure Q1 stays constant because it is the original muscle with no stretch. And the result of my experiment 1, we use the result to calculate the second equation to explain stiffness. And the pressure is calculated in the first. Use result in the experiment 1 for modeling the second equation. And about the muscle change, I think the balloon shape changed, but it doesn't affect that much. And about the stretching, you just mentioned that the sphere is not about the shape and the volume of it, but it is the epsilon. Because the epsilon, we just need to measure the vertical direction of the muscle to make sure that it is calculated in formula. And that's all. Thank you.
Okay. Questions from Yuri?
I have a question for all of you, because when we have a theoretic model, and just like the reporter, they use equation formula, and how did you evaluate your theory is correct based on the data?
Based on the data.
Yes, because you have a theory, and then you have observation, and can you evaluate your theory is correct or not based on the data? That's a very important step in inquiry. Because when you put your observation data in your Python code, okay, syntax, it always provides you the Q1, Q2, Q3, Q4, always will give you a set of values. But how did you know that's meaningful or not?
Because I have seen the references, and the references mention that it is to
Okay, I think that the answers can answer this question.
I believe that you should have a prediction, so a numerical equation, and then you graph it alongside your data to see, and then you analyze the data to see how well it fits.
They can use, it's already exists equation to double check it, and also use the Python and the reality, their simulation and the reality to compare whether it's suitable or not.
Because you use the equation to calculate your pressure, and use the pressure to expand your result. That's a kind of topology in your I see that. So you need to compare your data and your theoretical curve.
Yes, I did, but it's just, I think the Q1 to Q4 just fits the experiment I did, so I think it is.
So you based on the literature review, right? Your theory is from the literature. So at least you need to cite the references in your report.
I did, I put it on the page before the test. This one.
Maybe let me see. It's more straightforward. Just you think the balloon muzzle is the same as real muzzle, and does their data indicate the difference uniformly? Is my question clear for you?
Yes, you want to make sure that
Well, first of all, you think that the real muzzle is the same as the balloon muzzle. Then, does the data indicates the difference if they're different?
They didn't actually say the axial and the lateral changes.
No,
in
you think they're the
experience,
same? The real muzzle and the balloon muzzle?
but, they had mentioned that they used the string to.
Answer my question. You think they're the
I
same?
don't-
If no,
in lateral
then-
they are the same, but axial they didn't mention about it.
You think, okay.
Sorry.
How about you?
I don't think.
Oh, okay. The second part is, does the data indicate that?
I think their classification of the characteristics of the muscles don't align because they were very unclear in behavior.
How about you?
I disagree with the opponent because I don't think it's the same. You can see that the realistic muscle is just not
Oh, okay.
in your skin.
It's not the same. Does your data indicate the difference?
Yes, I think it does because because the number of them is different, and this one is not very close to the real muscle, and so does this one.
Okay, because of time. You want to add just very short?
In my experiment, the ear muscle is same as the biology muscle. That's because that the axial part will expand and the lateral one will shortening, and that's the same as the biology muscle.
Thank you.
Okay. So please prepare the question. For the reporter, 6, 6, 5, 5, 6. For the opponent, 6, 8, 6, 6, 4. And for the reviewer, 7, 7, 6, 7, 6. Okay, so step 2 is over. So let's take 10 minutes break. Okay, only 10 minutes.